you to Daniel Martinez. Daniel Martinez is actually a material expert. They have a company by the name Copper 3D, and they have been able to develop antimicrobial materials, which are used in various different applications. I'm sure it would be a great session where he will be presenting on various new materials. Now, the properties is to do with copper. So these are materials which will actually can be used in various applications, from medical devices to prosthetics. And I'm sure with more insights coming from Daniel, I think it would be good to know how his materials can be used with 3D printing going forward. Thank you.
Thank you, Dr. Shivu. Do you hear me well? Hello? Do you hear me? Yes? Perfect. So I'm going to start. Thank you very much for the invitation, Dr. Shivu John, to this Congress, International Congress. My name is Daniel Martinez. I'm the Director of Innovation of Copper 3D. And in this talk, I'm going to talk about the role of antimicrobial materials in the biomedical 3D printing sector, okay? So we are a Chilean company. This is Chile. We are located in the southern part of South America. This is our country. This is a funny shaped country with 19 million of people, a GDP per capita of $27,000. And basically we are experts in two things. One of that is wine and the other one is copper. In fact, Chile produces around 6 million tons of copper annually, which is basically 35% of the total world production. But the problem with this historically in Chile is this. We produce it and export copper with no added value. Basically, we export raw copper, okay? But that situation is changing right now. And we have, on these days in Chile, around 60 companies doing great things in terms of antimicrobial solutions based in nanocopper technology. And Copper 3D is one of that companies. We are right now a Chilean US company with a global presence. We are selling our materials in basically more than 50 countries. And our innovation is in antimicrobial additives and antimicrobial materials. Okay, we like to say that we hack materials to save lives. That is like our mantra, our purpose as a company. And how we started this journey? Basically, we started in this with problems that we saw in this field, in the traditional prosthetics and orthotics field. In this slide, you can see one of these problems. But the problem that got our attention was dermis complications and bad smell. We asked ourselves why this has happened, and the other thing that got our attention was that the 3D printing sector is rapidly introducing in this field of prosthetics and orthotics. But the problem with that is the high bacterial burden that we can find in these 3D printed medical devices, orthotics and prosthetics. And these are some of the complications that you can find in the literature. And these dermatitis, folliculitis, fungic infections, bacterial infections, with an estimated cost of more than $28 billion. This is just in US, and this is annually. So this is a huge problem around the world. And the problem with prosthetics and orthotics in the 3D printing sector is basically this. They are in direct contact with the skin. These are porous materials. These are complex geometries. Okay, so they are difficult to clean. But if you go deeper in the problem of bacterial burden, you will find this, that basically 10%, this is the data of World Health Organization, but basically 10% of all the patients in the world will get infected because of the treatment that they receive in the hospital. Okay, this is just the data from US. This is annually 2 million of patients infected, 100,000 of them dies, with direct cost to the system of $45 billion. So it's a big problem. And when you go to this problem, like you make a double click in the problem, you will find that at least 50% of this infection could be explained because of bacterial contamination of medical devices. Okay, so when we started this journey, we have this challenge: how we can create 3D printed medical devices with antibiotic properties. Okay, that was our final challenge as an innovation project. And then we can find very quickly that to make this happen, we have to hack the material. We have to intervene the material. We have to make something to the material in order to behave as an antimicrobial material. Okay. And again, we are in Chile. We are expert in copper, and we started to investigate, to make a research around the antimicrobial activity of copper, and we found very interesting things. This is a slide that shows. This is shows the results of a paper of Bill Keevil, which is a world-renowned researcher from the New England Journal. So this paper basically shows the antimicrobial action of copper compared to bronze, zinc, and steel. And you can find that in around 1 hour, the CFU, like the colony-forming units of bacteria, can drop drastically until almost zero. Okay, and why is that happen? That happened because of this. Basically, copper has 4 mechanism of actions to eliminate or to kill a bacteria. And these mechanism of action are listed here in this slide, but basically the copper releases copper ions, and these copper ions break the membrane of the bacteria. And once inside the bacteria, break also the DNA or the RNA of the bacteria. But we're talking about here, this is the scale that we're talking about. In the graphic, you can see a nanoparticle of copper in the upper side of the slide. But we're talking about a particle that is less than 100 nanometers. So that is basically the size of the virus or the DNA chain or a protein. So we're talking about really, really tiny things. And this is some of the results that we have of our materials in different laboratories. You got there the graphic of bacterial growth reduction over time in 2, 7, 10, and 20 minutes. And you have a wide range of microbes there, Escherichia coli, Salmonella, Pseudomonas, etc. And you can find that around 20 minutes, you have almost all that colonies of bacteria dead, are eliminated. Okay, and the problem, the question now is, what about viruses? Copper can eliminate or inactivate a virus, and the answer is also yes. There is a lot of information, a lot of scientific data on the antiviral activity of copper, and you have a couple of papers cited in this slide from Ham and Borkov. And they can validate that copper also has antimicrobial and antiviral activity in SARS-like and SARS-CoV-like viruses, and also in influenza. And they are in this paper, they are talking about after 5 minutes or even less, after 30 minutes of contact with copper or nanocopper or cuprous oxide, they have a very effective antiviral activity. Okay, so based in this information, we think that we can use this powerful concept of antimicrobial activity of copper, antimicrobial additives, to hack the materials that are being used in the 3D printing sector. So we, in 2018, presented the first antimicrobial 3D printing materials portfolio, which you can see in the right side of the slide. The first material that we launched was PLA active, and then MDFlex, which is the first one is PLA and the second is TPU, with full antimicrobial properties. And now I wanted to show you these results that we conducted in the Institut Pasteur of France against coronavirus, human coronavirus. And on the right side of the slide, you can see the activity of the additive inside the materials. And the action is super quick. You see at 5 minutes, you can see a 90% of reduction of human coronavirus. This is the strain that they tested. And then at 60 minutes, you can see a 99.975% of reduction of human coronavirus. So it's nothing, almost nothing there. And from there, from 60 minutes to so on, you can expect to find no viral burden in this kind of active materials. And again, this is the action that explains the powerful antiviral action. Basically, what these materials does, they release copper ions, and these copper ions generate a rupture of the envelope of the virus, and once inside, they break or they denaturalize the RNA of the virus. Okay, so these are very, very effective materials, and now we have this evidence, this laboratory evidence, that our additives and our materials effectively eliminate coronavirus. So that is huge for us. It's very good news. And this is one of the milestones of our company. In 2018 and 2019, we win two research funds from NASA to investigate the properties of these materials in order to 3D print antimicrobial medical devices in the ISS for astronauts. So that news goes around the globe very quickly, and that put us in a very good position of credibility and endorsement because of this research fund. Right now we have collaborations with a lot of companies around the world. These are basically research collaborations and commercial collaborations, and we have a huge network of distributors and resellers. In India, we are distributing with Novavins, and now we are reaching around 50 countries around the world. And we are also being considered on the top 5 additive manufacturing startups, which is a great honor for us to show also this achievement for our company. In terms of the cases of use of copper 3D technology, you can see a lot of companies doing great things around the world with our materials. We have, for example, companies in UAE doing antimicrobial ATM buttons. We have other companies doing cell phone cases, antimicrobial cell phone cases, doing masks, doing door handles and covers of a lot of kinds. And we have also companies doing these kinds of applications, antimicrobial frames for surgeons, antimicrobial toys, This is another picture. Antimicrobial kitchenware, insoles for diabetic food and patients, on obviously antimicrobial medical devices, simple medical devices, and other more complex medical devices like these or this. This is from a Korean partner called Real Dimension, and this is from another partner. Is the Alder Hey Hospital in UK. They are doing a lot of great things with our materials also. So I want to present you now the things that we are really proud of. And these are really nice projects that we are working from the last 2 years. And they fill us with proud. These are very nice works. For example, this is the first time in the world that a company make antimicrobial personalized 3D printed toys for children in immunosuppressed in ICU units or in cancer units. This was made with another company called Art Listo at the hospital, the Children's Hospital, Dr. Luis Calvo Maquena in Santiago de Chile. And basically, what we can do is a process where we take a picture, a draw of a children, and then we can go to a 3D model, and that 3D model we can 3D print with our antimicrobial materials. And this is the final result. This is the first time that the company made something like this, and it was really a pleasure to participate in this project. And now we are working on another project to tackle these big problems. One of them is diarrheal disease, which is basically people that has no access to clean water. This is a huge problem around the world. It kills basically more than 1 million people annually, and 25% of them are children with less than 5 years, living in countries in Africa and Southeast Asia mainly. So we come up with this solution, which is a collapsible antimicrobial and viral inactivation maze system. We inspired by biology, because we need a high surface of contact between the contaminated fluid and the material. And how to achieve that is with biology-inspired design. Basically, we inspired by the cerebral gyrus or the intestinal villi to make a design like this. This is a prototype. This is the first digital prototype, but basically this is a bottle where you can find an internal structure, which is this blue structure. And when you see inside the structure, you can see a lot of rugosities, and that rugosities can expand the surface of contact in a factor of 10x, around 10x. This is a video that shows the digital design of this concept. From the outside, you can see a regular bottle for water, but when you go inside, again, you can see this maze structure system with all these rugosities. And the idea is you can pour contaminated water here, and you can expect to be clean of microbes. This is not for filtering particles. This is for killing microbes, and you can expect to act in between minutes and less than 1 hour. Okay, so this is a very disruptive idea, and one of the work that we are very concentrated right now to validate. This is another project that we participate last year. This is to prevent mother-to-child transmission of HIV, which is around 40% of the total cases. Okay, and this problem generates around 300,000 people contaminated annually. Okay, so we come up with this the same concept, the same idea. These are the first digital prototypes, and the idea is to this is basically a shield. This is an interface between mother and child, and the idea is to, again, to prevent the pass of contaminated fluid, in this case breast milk, from the mom to the child, to the baby. And again, we use the same concept. We wanted to expand the surface of contact between the active material and the contaminated fluid, and the idea is to circulate this contaminated fluid, this breast milk, from this device, and on one side you get contaminated HIV milk, and on the other side you have HIV-free milk. We tested this in the microbiology laboratory of the Universidad de Chile, with excellent results. So the concept works. Basically, you can like filter or eliminate viral load from a fluid, but you need a flow of this fluid for this kind of structures. Okay, with active materials. So and this could be a concept of what we are thinking about. Okay. So we are working on that project on November and December of last year, and then comes the pandemic, and this was a terrible situation for all of us, very exponential in terms of people getting infected and people dying. This is the graph between January and April this year, and it's incredible to see an exponential curve of the new cases of coronavirus. This problem got another problems, like the global shortage of N95 surgical mask, exponential increase in contaminated mask waste, a global shutdown of distribution channels, we were thinking about the possibility of articulating some exponential technologies to generate a global impact. So we were thinking about these exponential problems need obviously exponential solutions, and that's why we launched this concept of an antimicrobial 3D printed mask in March 17 this year. This was an open source and an open source design, free to download. And the interesting part for us, this got a lot of attention, a lot of media attention, and around 7.5 million downloads the first week, and more than 20 million downloads up to date. Okay, with a lot of media coverage and great feedback from around the world. But this first model has a lot of things to improve, and that's why 2 weeks later we come up with another iteration of the original design. This is basically a monoblock. This is a closed structure, a hermetic structure designed to go outside the printer, like you see on the screen. This again, this new model, this 2.0 model, evolutionized to this new concept of an antimicrobial mask, but this is not 3D printed mask. This is a injected mask. This is made with a more industrial way. And this is the mask that we are right now working here in Chile and selling in a lot of countries. And there you can see the evolution, the quickly evolution from the first iteration, which was a flat structure that then you have to build and to assemble, and then to a more final product which we injected in with antimicrobial injection molding. Okay, so this project got a lot of global attention. These are some of the apparitions in international media. And what happens here is basically we started to work with a strong purpose and a big challenge, which is basically the global shortage of masks in a very complex situation, which is a pandemic. And we started to use some technologies that they call exponential technology, like nanotechnology, smart materials, or antimicrobial materials, solution-focused design, 3D printing, laboratory tests, with beta launch, with feedback from around the world. Very, very quickly, we can learn about the feedback from a lot of people from around the world, and then launch an open source design with massive downloads that generate distributed manufacturing of what we designed here in Chile. That was very interesting because from Chile, from Santiago de Chile, we can very quickly impact the total world with a solution when the world was in a crisis without solutions. So it was a great project for us, a great learning, a great experience, and we are very proud of what we achieved with this project. So what's next for Cooper 3D? For Cooper 3D, we are working right now with Petrochem, which is the biggest distribution company of polymers and petrochemicals in the Middle East, and we are making a joint venture which we'll call Cuprionics. What is Cuprionics? Cuprionics is a company that will develop, will manufacture, and will commercialize additive, antimicrobial additive, which is the additive that use our materials right now. But the idea is to put this additive into another solutions outside the 3D printing sector. And we're thinking about a solution for airports, for example, antimicrobial trays, antimicrobial trolley handles, antimicrobial surface on counter, antimicrobial acrylic guard. And we are thinking about solutions for airplanes, for example, antimicrobial seat trays, or bathrooms, but you can think about antimicrobial packaging and solution for workplaces and offices, mom and baby appliances, mass consumption products, like, for example, antimicrobial cell phone cases, or maybe kitchenware. So we are very concentrated as a company right now on 3D printing on the one side, doing more research on our materials, and the idea is to launch in the next weeks new materials, new polymers for different kind of technologies into the 3D printing sectors. And with this Cuprionics company, the idea is to push this additive into another solutions into the more industrial sectors, for example, injection molding or thermoforming. Okay, so this is very good news. The Cuprionics is now a very well validated technology, and we want to put this technology to impact the world, basically, and big industries. Okay, so this is what we've been doing the last 2.5 years. This is a very young company, and these are my coordinates if you want to send me a mail or ask something else. And this is Cooperative D is our website, and these are the social network if you want to know more about this technology. I don't know if you have some question right now or want to discuss something. Yes. Any thoughts on coatings and orthopedic implant? Absolutely, yes. That is one of the sectors that we want to push with these additives and materials. One of them is coatings, and the other is paintings. Not only for implants and orthopedic implants, but also for example, for furniture on surface on hospitals. Because, for example, if you go to an ICU, there is a high possibility to contaminate with the surface that you have around. So that would be a great addition to have a hospital with paintings, coatings, and medical surface medical devices with antimicrobial properties. Yes. So the answer is yes, Dr. Lalit. Anything else? Felipe wanted to ask something. Yes. Okay. Please, shoot. How long does the copper ions release last? That is a fantastic question, because the interesting part of the technology that we have is that we come up with a solution that can control the rate of release of copper ions. If you don't control the release rate, you can expect that the material could be could be useful and antimicrobial no longer than 1 year, okay, maybe 1.5 years. But when you have this new kind of additives that avoids the agglomeration and you can control the rate of liberation of this copper ion, of the release of these copper ions, you can expect this to be antimicrobial at least 5 years. We tested this in an accelerated protocols to be even 8 years antimicrobial, and from the year 8 and so on, you can expect a little decrease in the activity of the or the release of copper ions. So the answer is, with this additive, you can expect at least 5 years. The average is 8 years of full antimicrobial activity, and from 8 years to the future, you can expect a little decrease in the antimicrobial activity of these materials. Very good question, Felipe. Have you had devices printed and used for surgical purpose? The answer is yes. There is a surgeon here in Chile that is working on surgical guides with very good results. But this is, again, we are starting this journey. We are in PLA and TPU, and PLA is not I think it's not the proper material to make a surgical guide. So the idea is to advance, to move forward to more sophisticated materials like PETG or PEEK or PIC. And the idea is to have in the next months antimicrobial more advanced materials like PETG or PEEK. Regarding the hypersensibility issues, that is another very good question. We have our materials are certificated with ISO 10993, which is the biocompatibility certification. So these materials are no cytotoxic, they are not produce irritations of the skin, so they are very, very safe to use with patients. The cost many times the normal material? Another good question. For example, our material, let's talk about PLA. PLA, it's around $90 the spool, and the regular PLA could be, I don't know, $20 or $30. If you talk about a really good PLA, it could be $40, and this is more than the double of that price. But you have an excellent material that you can use for. This is obviously not for prototypes, not for toys. This is for more high-end applications. So, and the other thing is that the cost to produce this additive is high. So you can expect to have this antimicrobial material with the double of the price of the double or maybe the triple of the price of a regular material. Great question, Dr. Lalit Maini. Can normal FDM printer use it? And the answer is yes. In fact, we have tested this material with very high-end printers, but with very low-end printers also, like the typical, for example, the typical Ender 3 Pro, which is a very cheap machine, Ultimakers, Sword Tracks, and any kind of machines, of printers, and with very good results. In fact, some of the pictures that you see in my presentations were 3D printed with an Ender 3 Pro, okay, which is a very cheap machine. Yes, Felipe, absolutely. We should talk. I don't know if I can talk today, but for sure you can contact me by LinkedIn. I don't have any problem to talk with you. So the melting temp is similar. Yes, that is another good question. The melting temp is similar with the regular PLA. The other important thing that I want to discuss is if you add if you put this additive into PLA, you don't you can expect that the PLA behaves as the regular PLA. So basically, in other words, this additive don't alter the mechanics or the mechanical properties of the base material, which is in this case PLA or TPU. So the temperature is similar, the mechanical properties is the same. So you can use it in a regular printer and then you can use very very safely with patients or animals if you want. Thank you very much for your comments, Felipe and Dr. Lalit. We can stay in touch. You can find me in LinkedIn. Daniel Martinez Pereira is my name, and please feel free to reach me. I'm happy to discuss more topics, more things with you on the next days. Okay? I have to go, so bye-bye.